The construction of an MO diagram for carbon dioxide. We'll start with a pictorial view of the orbitals on the central atom and the terminal atom. We need to define what the point group is for the molecule. CO2 is linear. Officially belongs to the D infinity H point group because of its infinite rotation through the bond axis. However, for the purpose of defining the orbitals, we will approximate this to the D2H point group. Let's look at the atomic orbitals on the carbon atom, the central atom first. So we'll draw on some coordinates. It has the 2s orbital, pz orbital. We'll draw the px orbital in this way, and then it also has the py. So these are the orbitals that the carbon has to work with to form molecular orbitals with the atomic orbitals on oxygen. The two oxygen atomic orbitals we will combine into group orbitals first, and then use those group orbitals to form molecular orbitals with the atomic orbitals on carbon. The group orbitals are going to be formed in a similar fashion to the way we would make the molecular orbitals in dioxygen, the diatomic molecule. However, the group orbitals will be separated in space. So here's the two oxygens separated by the carbon. We have the s orbitals on oxygen, and if you remember from the molecular orbital diagram, we can have the two s orbitals combine like this, with both orbitals positive, and then we can also subtract one orbital from the other. So this is analogous to the bonding and anti-bonding versions of the MOs we would form with the s orbitals in the O2 molecule, but now we're using the same sort of combinations to make group orbitals that will be used to bond to the carbon and CO2. We also have the pz, px, and py orbitals on the oxygen. Those will form their own individual groups. The pz first, so our pz groups have head-on orientation in this molecule. So one combination is this, and then we have the other combination with the positive and negative lobes pointed directly to each other. So this again is, these group orbitals are analogous to the sigma bonding and anti-bonding orbitals that would be formed in the oxygen diatomic molecule. And this time we're using the same combinations to form our groups. And finally we have the px groups, and here are those combinations, and the py groups. Now we can match these group orbitals to the appropriate orbitals on the central carbon. One point to make here before proceeding is that remember that we had for each atomic orbital that we used in oxygen, we formed a group orbital. So for our two s orbitals on each of the oxygens, we form two group orbitals. For our two pz orbitals, we form two group orbitals, and so forth. Okay, so which orbitals on the carbon do these match to? So you can do this by inspection. The first s group matches in symmetry to the s orbital on carbon. And here I'm just looking for appropriate overlap. We're not thinking necessarily about energy and appropriate energy of the orbitals yet. The pz groups also match in symmetry to the s. The two positive lobes of this first pz group will match with the s orbital, will combine with the s orbital. The second s group matches the symmetry of the pz orbital on the carbon. Notice the positive lobe of the pz orbital will match with the positive portion of the s group, and the negative portions also match. And our second pz group also matches the pz orbital on the central carbon. So the symmetries there match. So we have some possible group orbital central atom atomic orbital combinations that we can use to form molecular orbitals. Next, the first px group has appropriate symmetry to interact with the px atomic orbital on carbon. The second px group does not. In fact, it doesn't match any of the atomic orbitals on the central carbon. And the first py group that we constructed matches the py group, a py atomic orbital on carbon. And the second py group orbital set doesn't match any atomic orbitals in carbon. The px and py groups will form pi bonding and anti-bonding molecular orbitals with the px and py atomic orbitals on the carbon. So from this point, we could go ahead and construct our molecular orbital diagram by putting these atomic orbitals of the carbon and the group orbitals formed from the atomic orbitals on oxygen in at the appropriate relative energy levels, and then combine them in the cases where the energy and the symmetry match appropriately to form the molecular orbitals. But instead we're going to pause here and actually approach this construction of the molecular orbital diagram from a group theory approach. So we'll use group theory to construct an MO diagram for CO2. And the first thing we're going to do is the same thing as what we did before, was determine the point group for the molecule. We already know that. We did it previously, so let's just go ahead and write this in. We're going to approximate it as D2H. There's the character table for D2H, so let's put that in. We'll need that in just a bit. Next, we're going to assign x, y, z coordinates to the atoms, so we know how to perform the symmetry operations on the molecule, and also how to orient the orbitals on the molecule. And remember that the highest order rotation is assigned the z-axis, or the z-axis is assigned to the highest order rotation. So we'll write in our coordinate system like this. The x is in the plane of the my electronic paper here. The z-axis also, and then the y would be coming in and out of the plane of the paper. I like to draw in the orbitals on the terminal or outer atoms so that I can see how they're going to move. So we have the s orbitals, the pz orbitals on oxygen, the px orbitals, and the py orbitals. And I'm not drawing in the carbon orbitals. I won't need those at this point, but of course carbon would have the same 2s orbital set. Okay. Now let's construct reducible representations for the combination of valence s orbitals first. Once we've done that, we will also repeat for the p orbitals. We will use construct reducible representations for the combination of the p orbital sets. This will be used to find the symmetries of the group orbitals formed from those atomic orbitals on the terminal oxygen atoms. In the case of D2H and other groups with twofold symmetry, we can handle the px, py, and pz orbitals separately. So in other words, we can make reducible representations for the py, the px, and pz separately. We don't have to hit them in one go. Okay, so let's start with the S, oxygen 2s groups. The E operation leaves both of those oxygens unmoved, and so they will both have characters of 1 for a total of 2. The C2Z rotation, the z-axis goes along the CO2 molecule, along the bonds, and therefore will contain those oxygen 2s orbitals. So when we rotate on that axis, they're unmoved, and therefore we'll have a character of 2. The C2y and C2x, though, will both move the 2 oxygen s orbitals in space, and so their characters will be 0 for both of those rotations, resulting in 0 for both the C2 rotation along the y and x. Inversion, of course, moves them both in space as they invert through the inversion center, which is on the carbon. So characters of 0 for both. The sigma xy, that plane bisects the molecule in half, and so those 2 s orbitals on oxygens will reflect through the plane, exchanging with one another. So since they've moved, their characters are both 0. The sigma xz and sigma yz planes, though, contain the oxygen 2s orbitals, so reflection on those actually doesn't move the orbitals, so they each get a 1 for a total of 2 for the characters. And so this is our reducible representation for the oxygen 2s group orbitals. We can go through the same procedure for the PZ, PX, and PY. Practice that now. You can pause the movie and practice, see what you come up with. Okay, so we'll start with the group orbitals for PZ on oxygen. That has a reducible representation of 2, 2, zeros for the characters of the C2y, C2x inversion, and sigma xy, because the orbitals move in those cases in space. The sigma xz actually will contain both of the orbitals, so they'll be unmoved in reflection on that, so that'll have a character of 2. And then the sigma yz will actually bisect. Oh, actually, that will also, the sigma yz will also contain those 2 orbitals, and so that will have a character of 2. Next, the oxygen px orbital. It has a -2 for the C2z rotation, because that will actually flip the 2 orbitals over, sending the positive lobes into the negative lobes. So they will have -1 for the character, so -2. The next 4, move them in space, so they get characters of 0. And then the sigma xz contains both orbitals, so it will have character of 2 for the 2 unmoved orbitals, and then the sigma yz bisects those 2 orbitals, actually inverting them on reflection and giving them a character of -2. And then finally the py 2, -2, 0, 0, 0, 0. The sigma xz in this case bisects those 2 orbitals, so reflection will invert the 2 orbitals, the negative lobes going into the positive lobes and vice versa. for character of -2, -1 for each inverted orbital. And then the sigma yz contains the orbitals, so reflection leaves them unmoved and they get a character of 2. So those are our reducible representations for our group orbitals. Next, we're going to reduce each representation to find the symmetry of the group orbitals. In this case, the reducible reps can be reduced by simply inspecting the D2H character table. In other words, figuring out which of those reducible representations in the character table add. In other words, figuring out which of the irreducible representations in the character table add to give the reducible representations that we derived. So let's start with the 2s and the pz group orbitals on oxygen. They have the same reducible representations, so they'll have the same, they'll reduce to the same irreducible representations. Inspection of the table. You can try that now. You want to pause and see if you can figure it out. Okay, so it turns out to be the AG and the B1U. Those two irreducible representations add to give our reducibles for the oxygen 2s and 2pz group orbital sets. So our group orbitals have AG and B1U symmetry. Next, the PX groups reduce to B2G and B3U irreducible representations. You can add those two irreducibles and prove that for yourself. So they will have B2G and B3U symmetry labels. And then finally, the PY group set reduces to B3G and B2U. You can also take a moment and pause and show that to yourself. So those will have B3G and B2U symmetry labels. So now we know the symmetries of all the group orbital combinations. We have the S groups and the P groups. If we want to now, we can finally determine the symmetries of the atomic orbitals on the central atom, so on our carbon. And once we know those symmetries, then we'll know which group orbitals on oxygen they will match with to form molecular orbitals. The carbon 2s, we determine its symmetry and all the symmetries for the central atom simply by looking at the character table. We can do this really quickly. The central atom S orbital will always have the most symmetric symmetry label, which in this case is AG. The PZ orbital on the central carbon, we can look at the character table and find which irreducible representation has a Z on the far right column, and that's the B1U. So the PZ orbital will have B1U symmetry. The PX, notice the X at the end of the B3U symmetry label, and so the X orbital will have B3U symmetry. And then finally the PY on the central carbon has B2U symmetry. Okay, so those are the symmetries of the atomic orbitals on the central atom. Let's begin construction of the MO diagram. We'll start by adding the central atom atomic orbitals and the atomic group orbitals of the outer atoms at the appropriate relative energies. So let's add in this information again. We'll start a new page so we have room to write the molecular orbital. There we go. So the relative energies, you can look this up in your text. Minus 19 electron volts and minus 11 electron volts for the carbon 2s and 2b. And then, not surprisingly, the oxygen orbitals are lower in energy because of the higher nuclear charge of the oxygen. Minus 32 electron volts and minus 16 electron volts. So we'll start with the carbon central atom on the left-hand side and our oxygen group orbitals on the right-hand side. We have the carbon 2s, which we showed had Ag symmetry. We have the carbon p orbitals, which have b1u, b3u, and b2u symmetry. Let's draw those in and label them. Okay, so those are the orbitals on carbon. Oxygen orbitals will be lower. In fact, the oxygen 2s groups will be much lower than the orbitals of carbon. Let's write the symmetry labels for those groups that we determine, Ag and b1u. P groups will be in between the 2s and 2p orbitals of carbon at minus 16 electron volts. And we have the labels in for the p groups on the oxygen atomic orbitals, so those are shown. Now let's combine our 3Ag molecular orbitals first. Since those are the lowest in energy, I like to start with those first. You can see that we have primarily two sets that will combine: the Ag atomic orbital, the 2s orbital, in other words, on carbon, and then the Ag group orbital formed from the p orbitals, the pz orbitals on the terminal oxygen atoms. The lower Ag group, formed from the 2s atomic orbitals of the oxygen atoms, is quite a bit lower in energy and therefore does not interact significantly with the other Ag sets. So primarily the molecular orbitals are formed from the upper Ag sets. The bottom one will be primarily a non-bonding and have oxygen 2s character. So those are our 2Ag, 3Ag, and 4Ag molecular orbitals. You can draw the lines in to show connections like that. Okay, so this is the first part. We'll take the 3b1u molecular orbitals that will be formed from the appropriate atomic sets. We have a lower b1u and an upper b1u for the oxygen groups, and then the b1u, the pz orbital of the carbon. Only the upper b1u of the oxygen groups and from the pz's and the pz orbital of carbon will interact significantly. The lower b1u formed from the oxygen 2s groups is too low in energy to interact significantly with the other atomic orbitals. So it will remain relatively unchanged and be a non-bonding orbital, much like the lower 2AG. And then we'll have the upper B1Us from head-on interaction of the PZs form our bonding and anti-bonding orbitals. We'll label those 2B1U, 3B1U, and 4B1U, keeping in mind that the 3B1U and the 4B1U are formed from the best overlap of the atomic orbitals and atomic group orbitals of the carbon and oxygen atoms. Put the lines in to show the connections. And next, the px and py orbitals will form pi bonding interactions. Remember, those had B3U and B2U symmetry. They'll form the pi interactions with the oxygen orbitals, and they'll be at the same energy. They're only different in their orientation, 90 degrees to each other. Those are the orbitals, the group orbitals and the carbon atomic orbitals. And so we'll get the pi bonding interactions. We'll label those B2U and B3U for the molecular orbitals, and then draw in those connections. And then finally, the B2G and B3G group orbitals, you'll notice, do not match any orbitals on carbon. We saw that previously when we were actually sketching out the group orbitals and atomic orbitals. Those will move over as strictly non-bonding orbitals in our diagram. So that's our completed diagram. Finally, we fill in the electrons. We have 16 electrons total, 6 from each oxygen, 4 from the carbon. We fill those in at progressively higher energy molecular orbitals. And what we find is that we have 4 non-bonding pairs, shown here, and then 4 bonding pairs, shown with the blue asterisk. So this matches pretty well the Lewis structure, actually, which shows 4 lone pairs and 4 bonding pairs. Of course, the distribution of the electrons is different in the molecular orbital diagram than it would be in the Lewis structure. Okay, so that's the derivation of the MO diagram for CO2 via group theory.